And welcome to the YouTube channel D Creations Resources. We are looking at different aspects from spectroscopy. We have been specifically talking about Fourier transform infrared spectroscopy in past few episodes. Today let us talk about the FTIR spectrum of HCl, that is hydrochloric acid. Now it's a classic system to study, and HCl, as you can notice, is a diatomic molecule, hydrogen and chlorine, and the bond involved is of course polar covalent bond here. Now HCl being a diatomic molecule, it can vibrate in one way, only one way, the hydrogen and chlorine atoms oscillating back and forth along the bond axis. Now this vibration is quantized, that means it can only exist at specific energy levels. Now HCl can also rotate around its axis, and these rotational motions are also quantized. That means they can also occur at specific energy levels. Now, as is the procedure in FTIR, infrared light will be incident on the sample, which is hydrochloric acid here. And when this infrared light interacts with HCl, it can excite the molecule from a lower energy level to a higher energy level by causing it to vibrate or rotate. And this absorption of light, which takes place, is what is seen as the spectrum. Typically, when you look at the spectrum, you can notice rotational fine structure. That means there will be a central vibrational line, and around this line there are closely spaced lines on either side due to the changes in rotational energy levels accompanying the vibrational transitions. And this fine structure in fact provides information about the molecule's bond length and rotational inertia. Now, the chlorine is known to exist as two isotopes, chlorine 35 as well as chlorine 37. So, both of them are going to have a slight difference in the masses, and this causes slight difference in the vibrational and rotational frequencies. So, you can see a split absorption line. Now, you will be able to determine several things from the FTIR spectrum of HCl. You can determine the vibrational frequency, the rotational constants which are related to the molecule's bond length and moment of inertia, the force constant of the bond, which basically describes how strongly the atoms are bound together. The main thing that you notice, of course, is a series of peaks arising from both vibrational and rotational energy transitions of the molecule, specifically the stretching of the HCl bond. And the prominent feature is the HCl stretching vibration, which absorbs infrared light at around 2500 to 3300 centimeter inverse. So in this range, somewhere in this range. And additionally, you will also observe a more complex pattern of peaks due to the rotational energy transitions associated with each vibrational state. Now, the most intense peak, of course, in the spectrum is going to be the one corresponding to the HCl bond stretching. And this vibration, in fact, is the molecule's primary way of absorbing infrared energy. Then this HCl stretching vibration is accompanied by a series of smaller peaks on either side. These arise from the molecule's ability to rotate in addition to vibrating. Each vibrational state can exist in various rotational states, leading to a fine structure. And as mentioned earlier, because chlorine has two common isotopes, there will be a set of peaks for each. The HCl molecule containing chlorine 35 will have a slightly higher frequency, that means shorter wavelength HCl stretch, than the one containing chlorine 37. So like any other FTIR spectrum of HCl is a fingerprint for the molecule, and mainly fingerprint of the vibrational and rotational energy levels of the molecule, and it provides information about the strength of the bond and how the molecule interacts with the infrared radiation. The main thing to remember is, because HCl molecule can be modeled as two nuclei connected by a spring representing the interatomic force, you can call this system a non-rigid rotator, and the nuclear motion consists of simultaneous rotations and vibrations. The non-rigid rotator has nearly independent harmonic oscillations and rigid rotations, and the vibrational energy levels can be predicted based on the molecular bonding strength, that is from spring force constant, and the rotational energy levels can be predicted based on the bond length, that is the equilibrium spring length. As mentioned earlier, in case of HCl, the simple physical model is that of the atoms which are considered to be points of mass held together by weightless elastic springs. Now, classical mechanics gives the corresponding vibrational equation of this molecule, and the solution is represented by a sinusoidal motion of two masses at a frequency determined by their masses and the restoring force of the spring. Although the potential and the kinetic energy of the system continually interconverts during the vibration, the sum of both energies, of course, is kept constant, just like a pendulum. Visualize two masses, say M1 and M2, and which are connected by a spring which has spring constant K, and R0 as the equilibrium distance. Now, as expected, the potential energy of this two mass model is going to be a parabola, and it's going to be harmonic, and the further the masses are displaced from their equilibrium position, the higher will be the potential energy of the system. And as you know, the equation nu is given as 1 upon 2 pi under root k by mu, where mu is the reduced mass, which is given as product of two masses m1 and m2 divided by sum of two masses m1 plus m2. And nu is the classical vibrational frequency of such an oscillator. Now, the quantum mechanical description of the harmonic oscillator can be used for describing the vibrational motion of a diatomic molecule like HCl. It's a heteronuclear diatomic molecule, unlike say Cl2, which is homonuclear. Both the atoms are same, but here that is not the case. This is a heteronuclear system, and the quantized energy levels will be given as E is equal to h nu into V plus half. So you can also call this as EV for this particular value of V. So here h, of course, is the Planck's constant, V is the classical vibrational frequency, and EV is the energy of the vibrational state with quantum number V. And we can take any integer value starting from 0. Now, regularly the vibrational transitions occur from the ground state. That means V is equal to 0 to the first excited state. That means V is equal to 1. So, if you consider just this simple vibrational model, it would predict just one single vibrational band for a diatomic molecule. But what do you observe? You observe that there is a series of closely spaced bands for the spectrum of HCl. So why are there so many lines? Now these lines are because of the rotational substructure, and you need to also take into account quantum number J for the rotational energy. Now J also takes integer values starting from 0. So every vibrational level has a stack of rotational levels, and transitions take place from V is equal to 0 to V is equal to 1 with J changing by -1, then it's called P branch lines, and J changing by +1, in which case it is called R branch lines. Now there is also another branch called Q branch, but it is missing here because of the selection rules. So you see a gap between the P branch and R branch. And the rotational energy levels are going to be given as Bj into J plus 1, where B is called the rotational constant. Now if you know B, it can lead to the molecular structure determination or it can lead to the determination of bond length. Now, to a first approximation, the rotational constants B of the V is equal to 1, that means upper vibrational level, and V is equal to 0, that is lower vibrational levels, can be determined using the formula. Also, moment of inertia I is mu into r square, and where mu is the reduced mass. We will talk about the calculation of the parameters in the next episode. Thank you. Rj minus Pj will give you 2 into B upper into 2j plus 1. And as I mentioned earlier, j is equal to plus 1 corresponds to R branch. Delta j is equal to plus 1 and delta j is equal to minus 1 corresponds to P branch.